This is the lecture for Class 6, Geoprocessing. And in this lecture we're going to cover a really fundamental component of GIS, which is term geoprocessing or GIS analysis. And this is a very important part of GIS where we're actually manipulating our data as it comes into the information system. So let's take a look at some themes that we talked about last class, Class 5 themes. And we were talking about data coming into our GIS, into our system. And it comes in at the bottom of an information pyramid. And to get to a point where we're going to be a good decision maker with GIS, we start with the data and then we do processing to get to some type of determination at, say, a policy level or a decision-making level. And that's very much what's going to happen for week 6 when we're geoprocessing. Is we're going to have data that comes into our system. We're going to do a lot of tasks to that data, and it's going to result in a map that is going to be very useful beyond just looking at the data in its raw format. We talked about the 4 V's of big data. So we have lots of volume, velocity, variety, and importantly veracity. So at this point in time, big data is very valuable, but sometimes it's difficult to have a lot of faith in making a determination or a decision about the data in the system. And this is a problem that really plagues big companies right now, say like Twitter or Amazon, is how do you process the data that's coming into the system to make really informed, wise decisions? So sometimes the veracity of big data is not at the level that we would like it to be at. We house data. So this is a physical thing that's going on. So as we have more data, we need more spaces to hold them within servers. And this is an image of the site in Utah, the Bluffdale site. And this is NSA server farm, essentially. And all big companies like Amazon and Facebook, everybody has to develop these infrastructures now to house all this data that they have. So it's actually affecting something that's a landscape feature now. We have open data. Open data is sort of the corollary of these data conversations, big data. And lots of governments are opening their data sources now because they see the use in it for decision making outside of the governmental bodies. So individuals are empowered by open data structures now. And certainly as GIS users and analysts, we're really interested in open data because it gives us that much more to work with in terms of our inputs into a GIS. We talked about the 5 stars of open data, and a 1 star we're going to give to a PDF that somebody might send us by email or we might be able to find on the web. The problem with a PDF is that the information's there, but it's in a proprietary system that is hard to extract into a machine-readable format. We really have to do a lot of processing on the PDF to get it to a point where we can use it in GIS. Excels and CVSs are better in terms of attribute data. And sort of the gold standard up here is when we get to URLs and link data that's readily available online, that's organized in some type of indexed way that makes that data really easy to find on the web. We spent time with rosters. So we did a DEM roster as our assignment last week, and that's an elevation roster. And we can talk about rosters in terms of being either discrete rosters or continuous rosters. So the values, the way that the values are held within the roster becomes really important. We talked about the spatial resolution of rosters. Some are high and some are low, and based on what we're trying to accomplish in our GIS tasks, we can either use a low or a high. And just because it's a low spatial resolution doesn't mean it's a bad image per se or a bad input. It just means that we're going to be aware of that resolution, and it may actually be very appropriate for the purposes that we're going to use it. We don't have to always use just high spatial resolution imagery to come up with really informed decisions from GIS. And this spatial resolution really reflects what's happening in terms of a ground coverage or a ground measurement. So if we have a 4-meter cell size in our file, that's really measuring 4 meters on the Earth, and we can see the difference every 4 meters from one pixel to another pixel. Whereas a 30-meter resolution, we have to walk 30 meters across a pixel on the ground to get to the next level of value, to the next possible value that would be held within the raster. So sometimes it's the same value, and say with elevation, if we're hiking up a hill, we're going to have to travel 30 meters to get to the next potential change in elevation. Whereas if we were using a 4-meter elevation file, we'd only have to walk 4 meters, and then we would be able to capture the difference from 4 meters in one spot to 4 meters in another spot. Okay, so we call Geoprocessing GIS Analysis, so we're introducing the GIS analysis tools today. That's what we're going to be doing. And we need to kind of talk about the background of geoprocessing. This image is from the late 1960s, early 1970s, from the Harvard Spatial Lab. And this is one of the locations where a lot of the original GIS framework was developed. And in this image, the person sitting the second from the right is Jack Dangermond, who was the founder of Esri. And I believe he's still the CEO of Esri right now. And here he is standing in front of a flowchart of map type information. And he founded Esri after working at Harvard Spatial Labs, and this is the software that we're using today. It's a multi-billion-dollar company. It's probably the largest GIS platform that's available in the market today. And what was decided upon early on in GIS is that we could process information in terms of a flowchart. That was kind of the form that data processing was given. So we would start with inputs. These are the blue icons. We would do something to it, which would be a tool, and then we would get an output. And once we get an output, we could either stop there and just make a map, or we could continue on our process and have that result be the start point for another series of tools. So we kind of link these tools from one set to another set. Now this last week we actually did do a workflow. We took elevation. Our input was DEM. We did a hill shade on top of the DEM, and we outputted that file, and then we used it in our final map as a layer, as the bottom layer, and then we put on top of that a thematic representation of elevation in terms of classing from a high to a low. So you class the values, and then you put the hill shade underneath. So we've done this. It's just a workflow. We did a small workflow this last week, but we can kind of link these things together, so we can do one thing and then do another thing and another thing. And the assignment this upcoming week, you go through a more complex process of processing data from a start to an endpoint. Okay, and we often call these things, so we input the data, we'll do some analysis, that's the second column here, so we'll buffer or union or merge something. And that'll often result in what's called a feature, which is essentially a shapefile if we're in vector format. And then we're going to maybe do some more analysis on it and produce another shapefile or another feature, and that'll get us to our final result. When we're doing these analysis steps, we're always trying to do one of 5 things, and these are kind of the classic categories of GIS analysis. So we oftentimes want to know where some type of value is. We want to know the most and the least of something. You know, what's the high, medium, and low of something. We want to know the density, especially with things like crime mapping or, say, contamination in environment. We want to know where the most dense of some thematic is located. We oftentimes want to know the inside and the nearby in terms of a distance from features. And we also want to know change over time. How are landscape features changing from one year to another year, from 1 month to another month, from 1 week to another week? We have 4 essential concepts that we're going to talk about in this lecture. The first one is selections, which we've actually done some already. We're going to talk about how GIS does measurements, and we're going to talk about a logic called Boolean logic, and then single layer versus multi-layer. So 1 layer of information or 1 layer of geodata versus using multiple layers. So we've done some selecting by attributes and select by location on our past assignments, and this upcoming week we're going to be doing that also. So here I have the cluster bomb site, which is one of the inputs this upcoming week for your assignment. And these are sites of, as the name suggests, cluster bombs, and this is in Kosovo. This is our assignment, which I'll explain in a little while. And we can select within the attributes of that particular data source. So that's, you know, we want to know something about the data in terms of how it's structured in terms of the table. We can also do a select by location. So if we wanted to know cluster bomb sites within, say, a district or within Kosovo itself, you know, the administrative boundaries, we could do that by layer. So that's using 2 layers to do selections. We will introduce the concept of distance this week. So so far we haven't really talked about this concept of how a GIS understands distance, but we need to focus in on it this upcoming week and talk about the 3 basic distances that GIS works well with. So the first one is the one on the bottom that I want to talk about. This is called Euclidean distance, and we can use the term as the crow flies to understand this distance. This is going from one point to another point in a straight line, regardless of what's happening in terms of features in a landscape. So we're not paying attention to roads per se, or walking paths, or some fixed way to get from one thing to another thing. We're just trying to figure out what's the actual distance across the face of the earth from one point to another point in terms of a straight line. And that distance, Euclidean distance, is going to be used for some of the tools in geoprocessing. And one of the tools will be buffering. So with buffering, we use a Euclidean distance. We also have what's called rectangular distance, which is at the top here. And as the name suggests, it's basically a right angle type of distance. And this is, we can understand it in terms of what's called taxicab distance or Manhattan distance. And those 2 terms come up sometimes in GIS literature. And what they're representing is when we're in New York and we're in Manhattan and we're in a taxi, we get from one place to another place based on a street network, and we're making left-hand turns and right-hand turns that are very fixed in terms of a path. And that distance is a much more complicated distance than just a straight distance. And that distance happens over a network. So say you're using Google Maps to calculate to get from one address to another address. Google Maps is not going to use a Euclidean distance formula to get you routed from point A to point B. It's going to use a rectangular distance based on the roads network that it sees in the system. So rectangular distance is always representing or referencing features that are within a landscape, say a path or a road, and they're usually human-made networks. The final distance is called a cost surface distance, and this happens primarily in a raster format, a gridded format, and what's happening here is that, let's say we're at the source and we have 3 ways to get to some location that we might potentially be interested in, A, B, and C. Each one of those paths is going to require a certain cost based on the cell values. And the classic example is just using elevation. So each one of our cell values in elevation has a particular number. And if we're going, say, on our first path, path A, if we're going from an elevation of sea level to Mount Everest, that's going to be a very costly path. That's going to be very difficult to get from that low elevation to that high elevation. Let's say between our source and path B here, we're just going from elevation sea level, 0, to 20. That's going to be a very low, least cost effective way to get from point A to point B, or I should say from source to point B. It's not going to require a lot of effort to span that elevation. Whereas C might be from going from sea level to maybe 500 meters high. That's going to require a little bit more than B, but certainly a lot less than going from sea level to Mount Everest. So when we're talking about cost over a surface, how hard is it to get from one thing to another thing? We oftentimes will use this raster cost distance formulation. So we're not going to talk about cost distance this upcoming week in the assignment, and we're not going to be using rectangular distance. We're only going to be using Euclidean distance. We are going to be using Boolean logic this upcoming week, and Boolean logic is shows up in a lot of different math formulas, and it's a common math type. It's a simple math type, but it's very powerful and popular. And the classic examples are A or B, A and B, or A not B. And this is a either-or type math. It's either going to be a 0 or a 1 in terms of its final formulation. It's going to be a very simple, either true or false type mathematical functioning. So in the first example, let's pretend these are map layers. So map layer A and map layer B, if we have everything inclusive, that's going to be one type of result, and that usually happens in what we call a union. In A and B, that's just the intersecting area between those two map layers, and we literally call that a map intersect when we're seeking that result. And then we have this other one called A not B, and oftentimes we'll be clipping out of A the area that would be in B. Okay, so these are different formulations, different logical arguments that are very precise, but they're also really restrictive. So we're not doing any fuzzy type calculations here. We're not saying, oh, something's close to A and it's a little bit close to B. No, it's either this or it's that. It's either this and that, or this or that. So it's very particular in how it's actually doing the math. We're going to talk about single layer versus multiple layer formats or processing. So with a single layer, in vector, we're usually buffering on features. And the input can be a line, a polygon, or points, or just one point. So in the in-class lab, we're going to use the centroid of Manhattan as one point, and we'll be buffering 1 mile on that point. And that's a single layer operation within vector. Okay, so we're just affecting, in that case, we're using one input, which is a layer, and we're outputting one particular feature, which is going to be our buffer. So it's single layer. And let's take a look at how that works in raster. In raster, a single layer is what we call a reclass. So when we're reclassing rasters, we're going from a series of pretty complex values usually, like the DEM that we were working with in week 5, where we had elevation that was very complex from cell to cell and different cell values from cell to cell. Now if we want to reclass that, if we want to put all the cells, let's say, are within elevation of 200 meters to 300 meters, well, we could reclass that into, say, a one number, into, say, 4s. And then if we wanted to know everything between, let's just pretend, 300 and 400 meters, we could give that a 5. And maybe everything right at sea level to 10 meters would be 1s. We could do that. And in reclassing a raster, we're simplifying the values of the raster to get to some end result. Okay, so we're usually doing it for a very specific reason. We want to clump values that are coming from our continuous surface and getting that into discrete values that are simplified but that are going to be very effective when we're actually processing our raster in a workflow. So now we're going to talk about two layers. What do we do when we're processing with two layers of information? And we're going to talk about how the vector and raster model treats that differently. So in vector, we call it a polygon overlay. Okay, so or a feature overlay. Okay, so it can be overlay of points and lines, but oftentimes it's polygons. We're overlaying polygons versus a grid overlay. So in a grid overlay, that's the raster format where as long as everything's sitting in the same coordinate system, we can take two rasters and put them together, overlay them. So here in the example for the vector overlay is that we have these line features. Let's just pretend it looks like these are roads or kind of cul-de-sacs here. And then we have, let's pretend this is a maybe a water's body layer. So when we overlay these two, we're going to treat the attribute table differently depending on what process that we're doing. If we're intersecting these two layers, it's going to treat the attribute table on the right differently than how it would treat a union. So here, if we smash these two together and just bring them together, and have them be really inclusive, A and B, layer A and B, that's going to give us a combined attribute table that is literally those two values within one attribute table. Okay, so it's just using two layers and outputting to a final layer based on those two incoming layers. And union, intersect, and clipping, these are three geoprocesses that we use between different layers of information coming into the system. And you'll be doing, I think, all three of these in your assignment this upcoming week, and we certainly cover all three of these in the in-class lab. In vector, we can union things, we can intersect them, we can do what's called an identity and symmetrical difference. We oftentimes clip, we can erase, and we can split things. So there's different tools that we can use. The classic ones that you'll use on a regular basis are union, intersect, and clipping. Now in vector, as long as our rasters are in the same coordinate system, in the same position, we can add those together. And oftentimes they'll be thematic. They'll be discrete. We'll have reclassed the values on the input side, and we can simply add these up. So say the first one is lettuce, tomatoes, and beef. As we bring it together, we're going to get a sandwich. That's kind of a funny analogy, but if we had one layer that was, let's pretend it was water bodies. So you're either going to be water or not water. The second layer might be roads. You're either going to be a road or not a road. And the third layer might be, let's say you're going to either be pine trees or ash trees. If we put all those values together, those thematic rasters together, what we're going to get back are arguments like areas that are outside of a road, that are a particular tree cover, that are outside of a water body, or it could be inside a water body, inside or outside of a road, and of a certain tree type. Okay, so we can bring those three together, and our final values then are it's going to be one of those three things within our first incoming rosters. The final output is going to be a combination of all three of those. And we can think of it as a simple math. Okay, so it's a Boolean or a logical operator that's taking place. So in this case, we're simply taking our first layer, our second layer, we're going to add those two together, and that's our final resulting values. So in this example, let's say that at this far corner, my grid 1 value is 2. At the far corner for grid 2, it's also 2. The final result right here in this cell would be 4. And we can see it over here. 1 plus 4 equals 5. 3 plus 2 equals 5. So it's a very simple type math that's being applied to the roster overlay. And oftentimes we can think about it as an input 1. An input 2 is then going to give us a simple output. And we do this thing called roster math. And roster math, or map algebra, happens in this thing called the roster calculator. And this is when we actually have two roster layers together, and we're actually creating new values based on those. It can be many inputs, roster inputs, or it can be just a couple. But it's a multiple layer roster input, and we're going to use what's called the roster calculator to do that. So that's very different. We're not going to use the roster calculator this upcoming week. We will use it soon in some assignments coming up. But for this first week, we're just going to be in vectors, so we're not going to be using the roster calculator. But we're going to be doing things that are similar to what you can do with a roster calculator. Okay, let's kind of do an overview of this assignment, of what you have coming up this week. I just want to talk about the broad themes and kind of the broad process. In some of the other videos, I go over some of the practical steps that you'll need. And then, of course, you have the assignment PDF that will guide you from the data all the way to the final part of the assignment. So the assignment is working with landmines and cluster bombs that are in Kosovo from the 1990s war in Kosovo. And this has become actually just within the last few weeks in 2015, in the fall of 2015, has become a big issue with the refugee crisis in Europe, where refugees are coming across the border into Kosovo, and they are potentially coming across these landmines that are in fields that have not been removed yet. So there actually is a lot of material that's still left out in the fields, especially landmine material, that hasn't been cleaned up yet. This is an ongoing process. A lot of it was cleaned up after the war by agencies, but it's still an ongoing effort. This is the Halo Trust. They've partnered with Google Maps. They're kind of a big nonprofit operator in Kosovo right now, doing this mine removal type activity. I'm just going to play this video to give an overview. They're using Google Earth as kind of their quote GIS to organize their data. It's robust enough for the techniques that they're doing. They're basically just capturing kind of a coarse approximation of the area. And then they're just using Google Maps or Google Earth to show that. This upcoming week, you're going to be much more precise in the way that you handle the incoming data. I'm just going to go ahead and play this so you kind of have an overview of the larger thematics of the assignment.
Kosovars are connected with their families and with their homeland. Too many countries fought for it. My father would be ready and fight. and go to the war. Myself, I think that's enough of the war. Still, we are in a war against mines. Halo is doing the best to take off the mines from the ground. We are committed to remove all the mines in Kosovo. We tried to take as much as information from the locals who saw signs that the area was dangerous. Google Earth makes our life much easier, defining the perimeter area that we need to be cleared. To the areas that we can't enter, Google Earth is a perfect solution. It's like flying over the task and define the borders. By taking all the perimeters and turning points in the ground, we place it on Google Earth and then produce the future clearance polygon. We are finding 100, 120, 150 mines per day. Personally, I believe that we have a great future. Nowadays, the people of Kosovo has got the highest amount of freedom that ever had. I hope they will have a better life and a prosperous way of living.
Okay, so that's kind of an overview of activity that's happening with Halo Trust right now, and they are active in Kosovo. The data that you'll be working with for your assignment this upcoming week actually came from the Mine Action Coordination Center, MACC, and they were very active in Kosovo after the mid-90s, and they did a lot of organization of the original data. So the problem is that there's nearly 1 million refugees coming back to Kosovo after the war. So this was happening in the mid-90s. And of course now, as I just mentioned, we have Syrian refugees coming across this material also. And the information is coming from the actual NATO bombing campaign records and military and civilian maps. So that's where the original data came from. And you're going to have two forms of the data. You're going to have landmines and cluster bombs. And those are two different type of ERW, but or remnants of war, explosive remnants of war, ERW. But they're going to be treated in the end in a similar way as either a safe place that doesn't have that material, or a bad geography or a contaminated geography that does have this material in it. We're going to do 3 steps this upcoming week to get to the final map. The first thing is that we need to figure out the severity of the hazards within Kosovo. So we're going to do that. Then we're going to identify areas that don't have much ERW in them, and those would be considered safe areas or simply none. In your final thematic map, it's going to have no, it's going to be a null value. It's going to have no particular contamination in it. And then we're going to set priorities in our final map by saying, here's districts. We're going to map to districts that are high priorities versus medium priorities versus low priorities versus safe zones or no contamination. And we're going to do 3 things in this assignment. The first thing is for the ERW, the explosive remnant of war, we're going to first buffer. So we're going to use a GIS process called buffering. We're going to buffer those particular input sources. We're going to union them together. So we have 2 types. We have both cluster bombs and landmines. We're going to bring those 2 together in a union. And then we're going to dissolve them. Okay? So when we dissolve them, what we need to do is we need to bring them all into one polygon. So there's one area that we're now going to call a bad geography or a contaminated geography. And when you do that, you're going to go from many polygons to one polygon. Now once we have this result called dissolve ERW, we're going to clip it to a district boundary. Okay, and when we do that clipping affair, what's going to happen is that it's going to separate out that one polygon into specific districts. Once it's in specific districts, we're going to calculate the area per district, and we're going to derive the percentage that's contaminated per district. And then once we have that number, that percentage number, we're simply going to rank that percentage number. We're going to say it's either high, a medium, or a middle value. It's going to be low, or it's going to be no contamination whatsoever, and we're going to produce a thematic map once we actually have that ranking established within our attribute table. So the input is on the left-hand side. When you open the MXD this week for your assignment, you're going to see, I'll just walk through them. The green line here is the municipal layer. Okay, that's the largest administrative boundary. Kosovo is the gray line, which is outside the actual outline of Kosovo going around, around the region and country. The smaller geometry here is the district level. So there's many districts within each municipality. Okay? And we have two BOM types. So this upside down red rectangle or triangle with a kind of alert icon in it, those are the cluster BOM sites, and those are actually lat-long precise coordinates. So that's where the NATO bomb campaign knows that they put down a cluster bomb in that particular location. And those are usually pretty close to cities. And then we have this little red dots and little red shapes. Those are the landmine locations, and those are more field-based. They're more disparate and spread out, and those are really causing a big problem now because a lot of the cluster bombs are kind of figured out where they're located, but these landmines, a lot of them are still sitting in the landscape, and that's the second type of ERW. So our final map from those layers, from those inputs, we're going to go to this thematic layer that's over here on the right hand side, and we can see we're going to map the districts. Remember, these are the smaller units, not the big green unit. That's municipalities. We're going to be mapping the districts, the smaller one, to high, medium, low, or none. And your final map should have this pattern. It should be the same pattern. So over here on the middle right hand side of Kosovo, there's not much activity. And then we have pockets where there's not much contamination. These light yellows up towards the top and up towards the, I guess that would be the northwest side of the country. Okay. So that's an overview of GIS processing. And this upcoming week, we're going to use it for a very practical, really interesting purpose, which is figuring out a priority for landmine removal. And this is an activity that's happening worldwide now in lots of countries, and GIS is being employed very dramatically to help solve finding these locations and then setting priorities of removal for ERW. So good luck this week, and I hope this lecture will explain some of the basic concepts, some of the processing concepts behind the assignment that are really important and central to GIS as an activity beyond just map making in and of itself.